What's up, math fans? Today we are looking at geometric sequences. So you have to already have seen the video on arithmetic sequences. Now, what's a sequence? A sequence is easily confused with a series because it's a list or a set of numbers, but a sequence is just a set of numbers with commas in between. It's like saying, well, first we'll look at the 1, then we'll look at the 3, etc. A series is when you have those same numbers, those same terms, but with plus signs in the middle because you're going to want to add them at the end. Right now, I don't want to add them. I just want to look at them, evaluate them, look for patterns. All right? So that's the difference between a sequence and a series. Right now, we're just looking at sequence. Also, when you're looking at arithmetic sequence, that means that the pattern is formed by either adding or subtracting a term to a number to get from one term to the next term. Geometric sequence is a little different. So let's look at it. If we're looking at these numbers, and by the way, these are my favorite numbers. The reason why I've told this story before, it's a movie I really like. The movie's called Pay It Forward, where one boy has an idea that he's going to help 3 people. Then he asks those 3 people to help 3 people, and the idea keeps growing, that everyone pays it forward. So that's where these numbers come from. Start with 1 boy, then 3 people, then 9 people get helped, then 27 people get helped, etc. So what's happening? How do I get from 1 to 3? When I first looked at sequences, I asked myself, well, what do I add to get to the next number? I add 2. But then I would have to add 2 again to get to the next number. It would have to be a constant rate of change, and it's not. So right away, it's not algebraic, but that doesn't mean it's geometric, so we have to make sure it is. So let me see, is there another way to get from 1 to 3? Yes, we're multiplying by 3. Let's see if it works again. Yes, it does. I multiply by 3 again, I multiply by 3 again, I multiply by 3 again. So instead of the common difference, I have a new vocabulary phrase for you. It's called a common ratio. It's what happens. How do I get from one term to the next? Common ratio could come from either multiplying or dividing, because that's basically the same operation. So here, my R would equal 3. Simple as that. It's very obvious to me. But if it's not obvious, here's a formula for you. The common ratio comes from a sub n over a sub n minus 1. That looks like a crazy formula. It's not. It just means pick a term and divide it by the term right before that, and that'll give you your common ratio. So if I pick 9 and divide it by the number before it, the term before it, 9 divided by 3 is 3. I could have picked 81 and divided by 27, still going to get 3. I could have picked 3 and divided by 1, still going to get 3. That's why it's considered a common ratio. It's just pick a term, divide by the term right before it. That's what a sub n minus 1 is, the term right before a sub n. All right, so I got my common ratio. I know that it's growing quickly. If you were to think of this in terms of a graph, my first term, this is my a sub 1, this is my a sub 2, this is my a sub 3, this is my a sub 4, this is my a sub 5. If you think of this as an XY table, my first term, second term, third term, fourth term, fifth term, my first term is 1, my second term is 3, my third term is 9, my fourth term is 27, and then 81. If you were to graph these points, how would they look? And I'm going to make a very ugly sketch here. 1, 1, 2, 3, 3, 9, 4, 27, and then 5, 81 is somewhere really, really high. And what's happening is that's exponential growth. It's curving up quickly. It's not growing at a constant rate like a line would. So that's another clue that you're looking at a geometric sequence because your points grow quickly, exponentially. If you were looking at an algebraic sequence, they would be growing linearly. Now the reason I'm not going to connect the dots, although I could connect the dots to show you that it's a curve, the reason you don't want to connect the dots is because once you connect the dots, it implies that there's points in between here and here, and there's points in between here and here, and there's points, and there's points. So now, if you connect dots, you're saying there's a point here, there's a point here, there's a point here, there's a point here, etc. Infinite amount of points. That's true in graphing. That's not true in sequences. There's nothing between the 1 and the 3. There's nothing between the 3 and the 9. So there's no decimals. So I wouldn't connect the dots. I would leave separated or isolated dots. All right? But there's your clue on when you're looking at geometric sequence. It's growing quickly. or exponentially. Okay, so I got my A1, I got my R, I think I'm good. Again, just like in an arithmetic sequence or an arithmetic series, same thing, there's a recursive and an explicit formula. Recursive formula, this time it says I get one term by taking the term right before it and multiplying by R. So I get to the 9 by taking 3 and multiplying by 3. I get the 81 by taking 27 and multiplying by 3. So any term I can get by taking the term before it and multiplying by my R, by 3. So you might see the formula like this. You might see the formula like this. This is my recursive formula. This is how I get from one term to the next. But one term to the next is a slow progression. What if I want to get directly to a term? Then you might want an explicit formula. How do I get to any term? Well, I take the first term. First term has to be given, or some kind of clue in a word problem, so that's 1 in this case. And I multiply by r to the n minus 1 power. So this time I'm going to multiply by, well, my r is 3, right? That's my constant, my common ratio. So that'll be 3 to the n minus 1 power. And that's okay, I don't need to know n, because n represents whatever term I need. If I wanted the 5th term, I'd plug in a 5 here. 5 minus 1 is 4. 3 to the 4th is 81. So that is my 5th term. If I wanted my 3rd term, I'd plug in a 3 here. 3 minus 1 is 2. 3 squared is 9. So my 3rd term is 9. The formula is flawless. All right? So you build yourself a recursive or an explicit, or both, whatever works better, or whatever the question asks for. All right, and that's pretty much it. So check out number 2. What do you think? Is it arithmetic or is it geometric? Well, let's see. How do I get from 100 to 50? You can say divide by 2, but if I was multiplying, I'd be multiplying by a half. How do I get from 50 to 25? Again, I multiply by a half. Oh no, I'm not sure. Where did that half come from? If you're not sure and you're trying to find R, if you're trying to find your common ratio, you just take any number, 50, and put it over the number right before it, 100, and that is, guess what, reduces to 1/2. It's got to work every time. 25 over 50 is also 1/2. So I got my R, I know my A1 is 100, so I can easily build both formulas. What's the recursive? Well, I get any term by taking 1/2 of the previous term. This would be recursive. Or I can get any term by taking the first term and multiplying by R, right? Taking the first term, multiplying by R, which we established is 1/2, and raising that to the n minus 1 power. And I hope this jogs your memory. If you did exponential growth, this looks a lot like y equals a times b to the x power, where a is the initial value and b is that rate, or we're calling it now common ratio, and x is of course wherever you're trying to get to. So if I wanted the 4th term or the 5th term, I just plug in 4 or 5 here and I figure out what my term is. Alright, so that's geometric sequences. Stay tuned for geometric series. Thanks for watching. See ya.